In a universe shrouded in mystery, where the stars are our only companions, a journey awaits that will push the boundaries of knowledge. Prepare yourself for something that will redefine our understanding of technology, unveil the secrets of the cosmos, and witness the marriage of human ingenuity and artificial intelligence. We bring you the flagship event of IEEE SIESGST, the Galaxy of Intelligence, Epsilon. A triad of scholarly symposium days guided by the wisdom of global pioneers and visionary minds. An event designed for everyone to gain knowledge and cultivate interest and curiosity. In this edition, we give you Narrow AI. Narrow AI is the concept of brainstorming events that have a significant impact on AI technology with humans like us, you, and me. We're not different, we are the same, with faraway souls. The concept of AI extends from the tip of your hair to the last cell of your nail. Computer vision. Computer vision excels in a field where robots outperform human vision. We will construct a future, the light of invention, together. Self-traveling dreams during the day and night. Algorithms flare in this world of pixels, revealing faces and emotions in the darkest night. With each step forward, we go closer to the future, the promise of computer vision and an unending flight. Deep space communication. MTTS ascends, passing across galaxies in its path. Deep space learning is a place where mysteries wait. As boundaries disintegrate, the cosmos is revealed. The brilliance of AI and technology, the resolution of a cosmos. We gather at Epsilon, braze eager and bright, in the light of AI to comprehend the cosmos. Prepare for an intellectual adventure like no other. Mark your calendars because the future awaits. Epsilon 2023 starts 30th September live on YouTube. Brought to you by IEEE SIESGST.
Hello, everyone. A warm welcome to each of you present here today. I am Akash, Creative Head at IEEE SISGST.
And myself Deepak, the technical head of IEEE SIESGST. We are your hosts for the day 2 of Epsilon 2023.
I can't express how excited I am to embark this incredible journey of mastering the computer vision with you.
Computer vision is altering our life in a way we never could have anticipated, whether it's through facial recognition, autonomous vehicles, or even medical image analysis.
However, before we get started, I'd want to make a few announcements. First, the session will be live for 2 hours. Following that, we will offer a link for the quiz. It will be based on the session from today. Make sure you take the quiz to compete and take the top rank on the leaderboard.
Let me now present to you today's expert, Mr. Rupesh Mahore. He is a researcher at Indian Institute of Science in Bangalore and explores computational physics, machine learning, and artificial intelligence. In addition to CERN and ISRO, Sir has also worked at Harvard University. Mr. Rupesh is an Indian government awarded physicist entrepreneur who has received recognition from Google, Meta, and Department of Science and Technology. Through his expertise, he has also created technology for people with physical challenges, for which Sir has honored with a special mention award by Enable India in 2022. Uh,
Hello, sir. It's pleasure to have you here today. Each of us is incredibly eager for the session.
Hello, guys. Thank you so much. Thank you so much for having me over here. It's glad to be a part of this event, and I'm happy to deliver whatever the knowledge that I have in the field of computer vision. And I hope that it embarks you on a journey to create new technologies in this field. So, yeah.
Now, I would like to turn the session over to Mr. Rupesh Mahore so that we can start.
Sure.
So now you can start the session.
Yeah. Let me just share my screen and let me start the session. I hope you are able to see the screen.
Yes, sir. It's visible.
Yeah. Yeah. So, hello everyone. Myself, Rupesh Mahore. I am a research associate at Indian Institute of Science, Bangalore, and I work with machine learning and computer vision. Computer vision is basically a bigger part of deep learning and CNN models that we work with. Previous to my conjuncture at IISc, I graduated with my BS/MS in physics from NIT Rourkela with a major in computational physics. And during my undergrad years, I worked at IIT Kanpur with Professor H.C. Verma. I worked at ISRO during the last phase of Chandrayaan 2 mission at Laboratory of Electro-Optical Systems. And 3 years back, I worked for around 6 months at Harvard University, working with computational simulation of polymer knots and stuff like that. And when I came back to India, I started working on a number of problems. One of the pertinent problem at that time was an oxygen conservation device that we worked with. It basically had a simple computer vision, a simple machine learning algorithm which optimizes the flow of oxygen and stuff like that. So, yeah, that's all about me. And let's dig deeper into the computer vision part. So I guess you might have had an idea about what computer vision is and how we view how a computer looks at an image and how it processes. So in this session, we will talk about how we use computer vision in different applications, and we will unlock the power of visual data. So the agenda for today's session is it is divided into three parts. First is a general overview about computer vision. In the second part, we will dig deeper into what convolution is, and in the third part we will get some hands-on. We'll get our hands-on dirty with some classification problem, image classification problem using Python. So we'll try to understand what computer vision is, what the real-world applications of computer vision, and what's the importance of computer vision in today's age and technology. So what is computer vision? Computer vision is a field of AI largely that enables computers to interpret and understand the visual world. The world that we see, the computer sees it in a different way, and we need to come up with algorithms, and we need to come up with methodologies through which this visual data can be understood by a computer in the way that we want, and it can extract the information from those images and from those videos, which we generally can't from our human eyes. Largely, it tries to mimic the human vision by enabling the machines to analyze and make decisions based on the images and videos. That's what computer vision, a clinical definition of computer vision is. And there are 4 key components in computer vision. The first thing that we do is we try to do the recognition of the image. Secondly, within that image block, we try to do the detection of objects. After detecting the objects, we do some image processing. The processing is also involved in the initial part, where we have to do the pre-processing in order to feed that information to the computer. And the fourth part is how we process it and what information that we try to extract from that processed data. That's where deep learning and machine learning comes into the picture. There are numerous applications of computer vision in our life, everywhere around us, starting from autonomous vehicles, healthcare, in medical imaging, in surveillance and security, robotics, augmented reality, and recently in metaverse and AR, especially related to retail store, to enhance the experiences of these retail stores and stuff like that. In autonomous vehicle, computer vision plays a crucial part. Tesla being one of the pioneer in the field right now with their latest computer vision models, which enables them to navigate seamlessly within a complex network of traffic. So computer vision is crucial for enabling vehicles to perceive and navigate their surroundings and make autonomous driving a reality. In healthcare and in medical imaging, computer vision plays a huge role. Usually when we used to have the images of, let's say, MRI or CT scan or X-rays, so doctors used to view those images, and based on his observation, his perception, they used to come up with insights. But with current computer vision algorithms, we can come up with better diagnostic tools. For example, during the period of COVID, a lot of researchers came up with methods to understand the degree of complexity of the COPD, chronic obstructive pulmonary diseases, which were present in the lungs based on the lungs, the X-rays of the lungs. So the computer vision algorithms can really leverage our diagnostic capabilities in ways we have never thought about previously. So computer vision aids the medical diagnosis and the treatment by analyzing medical images and detecting anomalies and assisting doctors in a much better way. Computer vision plays a huge role in surveillance and security. The post detection and facial recognition is largely a part of this domain, where computer vision enhances the security by monitoring and analyzing video feeds for suspicious activities and objects around. They are really useful in case of industrial setting also, where a company needs to maintain a certain compliance regarding the way workers are working in a factory. For example, if they are wearing a helmet or not, if they are wearing safety gears or not. So that is also where computer vision is really helpful. In robotics, computer vision plays a huge role in the current age of assembly lines where everything is almost automated. So we need a precise calculation of every single part that we are trying to, let's say, hold on with a robotic arm, or if we want to screw or unscrew something. So robots use computer vision to interact with and navigate through the physical world and make them more versatile. Computer vision is really important. So in last couple of years, AR and VR has been revolutionized by computer vision. The reality or the realization of metaverse and immersion in metaverse has been possible only due to computer vision. So it's booming there also, and especially in visual search that we usually do using Google Photos and Google Image Search. Computer vision plays a huge role in that also. So now we will move on to understanding what image is, and we'll try to do some basic calculations on images, and we'll try to get our hands on with image processing. So in this part, we will try to understand what digital images are, what are the image representation, common formats, and we will do some common image operations on sample images. So, what is a digital image? Well, by definition, digital images are representation of visual data in a digital format composed of discrete pixels, and they are, of course, ubiquitous to our daily life. And these pixels are short form for picture elements, smallest unit in a digital image, and these pixels are like these tiny dots that come together and form an image. Resolution, we talk a lot about image resolution when we deal with the images, and let's try a couple of things with some image processing, basic image processing operations. So let me quickly open my Google Colab notebook. So if you can see it. So what we will do over here is we will take a simple image from the data set that we have, and we will try to do a couple of operations on those images and try to understand what pixel values really are. So let me just quickly get these images from my folder. So, for example, let's look at this simple image of child playing in a wood. So, if you just look at the image, you get an idea about what the setting really is, what the environment is. Let me just open it again. Yeah. So from this image, you can see that there are four infants playing around, and the mood is jolly, and the weather is sort of, you can get an idea about maybe it is autumn or summertime, and they're playing in groups. But what a computer does with this image is really important. So for a computer, this image is nothing but a couple of pixel values. So for a computer, it doesn't know what a child is, what a wood is, or what summer really means. So for a computer, this is what the image really is, and that's all. That's basically what the computer interprets this image as. Now we want to extract meaning out of this image, this digital representation of pixels. So before coming up with meanings and before coming up with shapes and objects within this image, what we will try to do is we will try to do simple mathematical operations on these images. So these images are nothing but a matrix representation of the visual data. And with the matrix representation of this visual data, we can do some calculations on each pixels. And I'll introduce you to a very important concept in this field called as convolution. So the entire image processing pipeline and the fundamentals of all the deep learning algorithms that we apply on images and videos are at the end of the day based on nothing but convolution. So let me take you through what convolution really is. Just a moment. Oops. Yeah. So convolution is nothing but a mathematical operation in which we apply this mathematical operation on two functions in order to understand what is the overlap between these two functions. So this is the mathematical representation of convolution. Let's say we have two functions f and g. These are discrete functions, by the way. And if you want to apply convolution on these two functions, we basically take the product of two terms corresponding to certain index, and we take the sum over all the terms. So let's take an example and let's see how convolution really works. So let's say we have two 1D arrays. The first array is 1, 2, 3, and the other is 4, 5, 6, and we want to we want to do a convolution. We want to apply a convolution operation on this array. So the output of this array would be an array of size 5, because that's what the convoluted matrix will give us. And in order to find out the elements of the final convolution matrix, this is the operation. This is the operation that we will apply on each element. So, for example, the first element would be simply the multiplication of the first element, ai and summation of ai and bj, where I and j, the sum of j and I, should be equal to n. In our case, it should be equal to 3. So we will take the first element and we'll take the last element. So the first element of convoluted array would be 1 into 4. The second would be we will slide this a little inside, and the elements which would be multiplied over here would be the ones which are common over here. So the second element of the convolution array, a convoluted array, would be 1 into 5 plus 2 into 4, which gives us 13. Similarly, 28, 27, and 80. This would be the final convolution over the two simple operators, simple 1D arrays. So this is what convolution really means. Now the mathematical importance of convolution is in the fact that in case of 1D convolution, we don't really get a meaningful information out of it. We just are multiplying two 1D arrays, and we are sort of trying to understand if there is a correlation between these two 1D arrays. But in case of 2D, the meaning really changes, because we have a hell lot of information, and when we do the convolution of one 2D matrix over the another, we will get the features of the first matrix extracted over the second, and the resultant matrix will give us the feature of both first matrix filtered by the second matrix. So sometimes these filters, all the filters that you use on Instagram, Snapchat, or whatever, are nothing but some convolution operations that are being performed on the videos and the images. The convolution, the second matrix that you see over here, is called as kernel, and the first matrix over here is generally an image on which we perform the convolution. So when we take it to a 2D, in a 2D case, let's say we take an input image, something like this, and we this is our input image. This, it consists of an entire array of pixels, a 2D array of pixels, pixel values from 0 to 255, and we will take a kernel, or the second matrix that we took previously, and we apply this convolution over the entire matrix, and we will try to understand what result that we will get. So when we perform a convolution over a kernel of kernel which looks something like this, what we will get is actually edges being detected, or either the image would be blurred, or either it would be sharpened, right? So this is what convolution really is, and this is the actual convolution which comes into the CNN network that we talk about. So what we will do over here is we will try to do some basic calculations on the image that we had previously, and we will apply different kernels. Kernel is basically the second matrix which is being used over the main image, and we will see what results that we get. And it's really interesting what we can how we can manipulate this kernel and get different resultant values. For example, let's take an image of a coin. Let me just input that over here. Yeah. So this is an image of a coin. What we wanted to do is we wanted to apply different kernels over this image, and we will see what we will get out of it. So to start with, first we will take this image and we apply a kernel called as Sobel kernel. Sobel kernel is a kernel in which the middle part, or the horizontal mid-axis is 0, and the edges are either -1, 1, 2, or -2. So this is what the Sobel kernel really looks like, and what this basically does over an image is it extracts the features in such a way that each pixel of this image is changed in a way that the edges are being extracted. So, for example, what an edge really is let's say so in this image, an edge is basically a rapid change in the pixel values from a certain magnitude to another. For example, if we zoom in to this part, how our brain really interprets this thing as an edge is there is a rapid change in the pixel value from this pixel to this pixel, and we call this boundary as an edge. But how a computer really interprets it is in a way that it performs this convolution over this image, and what the output it gets is basically these boundary values. So if we apply this kernel on this image, so this is the kernel, which is this kernel is being applied to each pixel of this image. For example, as we saw over here in case of this. So this is our kernel. In case our kernel is a Sobel kernel, and it is being applied to each pixel of the input images of the coins that we have. And it will do some calculation, it will do some mathematical calculation, and it will generate another matrix, which would be our convoluted image. So in our case, what we will get is from this image, we will get these edges. Now, if you look at it, uh, if you look at the Sobel kernel once again, the middle part is 0, which means that when we are performing convolution over an input image, the middle part, which is like the main part, because the mid part, as you can see over the convolution function, has most number of elements. So it is basically the most significant bit in our entire process. So in case of Sobel kernel, this value is 0. So we really don't consider the value of each pixel, but what we are really interested is in understanding what is the difference in the values of the pixels that we are getting. So as a result of this Sobel kernel, the edges are being the edges comes into the picture. They appear more dominantly, and other parts of the images are just being turned into 0. So these regions are basically the regions where the difference in the pixel value changed abruptly. For example, over here, there was no significant change in the pixel value. Let's say if we move from this area to this area, so that's why this area was mostly black. But in case of here to here, there was a significant change in the pixel value. Hence, we got an enhanced version of that. Another interesting kernel is called as a Laplacian kernel. And if you look at the Laplacian kernel, this is what it looks like. Again, this is a simple 3x3 kernel. We can also use a kernel of any dimension with more resolution if you want a better resolution or a better quality of the image. But for the sake of convenience, we will just stick around to a 3x3 kernel. So in case of a Laplacian kernel, you can see that the corners of this kernel are actually 0, and the middle part, which is the most significant bit in our case, is -4, which is more significant. So when we apply this Laplacian kernel to our input image of the coins, let's see what we get. So we get even more enhanced edges, but the difference in this case and the other case over here is that these edges are not very sharp. They are very sort of blurry. But in case of a Laplacian kernel, what we got over here is very clean edges. Even the boundaries are being extracted in a very nice way. This is because the edges. Now the difference is not now the values of pixels. When we shift from one part to another, let's say when the kernel is moving from one pixel to another, since the significant bit is more enhanced, therefore the edges are being the edges that we get are more sharp and they are more cleaner. Let's try a couple of more things, and let's try something instead of making the kernel heterogeneous in the sense that all the values are different. Let's take an average of let's take an average value for let's basically keep the kernel homogeneous. Let's keep each and every value the same, and we'll see what will happen if the kernel over here is homogeneous. So if the kernel is something like this, which is like just containing 1 and divided by 9 because we want to normalize it. What you will get over here is this is the input image, and the output image looks something like this. So it is slightly blurred. So what happened over here is while the kernel was while we were doing the convolution over here, the kernel value or the value for each pixel for the output image was being the average of all the values around this pixel. For example, this was our original kernel applied over this pixel of the input image. If we apply a Laplacian, we will get different values. It was a heterogeneous kernel. But if the kernel was homogeneous, so this output value of this pixel would be nothing but the average over of the pixels that we calculate over here. So as a result of it, what we will get is our image being slightly blurred from the initial ones. So these are some of the simple operations that we can basically perform over here. Uh, if we so there are in Python we have some inbuilt functions for a much better extraction for edges and for better extraction of features from these images. For example, we have this filter. So this kernel is nothing but a filter, and this kernel can be of any size and of any type. So there's a kernel called scanning filter, where instead of just using a 3x3 matrix, we take a much larger matrix, which is an inbuilt function in Python. And what it does is it extracts very minute features within this image. For example, initially we were just able to get the edges, and these features were not being extracted more properly. But here we can actually extract all the features. For example, let's say we have a coin, or let's say we have a signature over here. We can actually extract the signature out of an image from very precisely using Canny filter. So yeah, these were some of the examples. One more example of a filter is called as a sharpen kernel. It is also a very simple kernel in which the kernel looks something like this. So here the pixel values which are present over the edges are just nothing but -1, and the significant bit over here is 9, which is quite large. So what happens as a result of it is that since these values are -1, so the pixel that we get in the output, this pixel is being so the information is being fed from all the it's being fed around this pixel, and as a result of it, the information over here is the pixel value over here is much more enhanced. So as a result of it, what we will get is a more sharpened version of an initial image, because this kernel is being surrounded by -1 values and a positive plus a large positive middle value. So what we will get over here is a much more sharpened version of this image. So this is basically how the filters work. You might have used it in a number of places: Instagram, Snapchat, PixArt, or some editing tools like Lightroom or Adobe Photoshop. So what they basically do is they just apply a certain kernel to an input image, and they get a convoluted image, and that's what basically the filters are. Now these image processing operations are really important, because they are basically a precursor towards feeding the information to a more complex network, like feeding the information to a machine learning model or deep learning model, and then trying to come up with more insightful informations from those images after doing some pre-processing. So let's quickly go back to where we were. So this is about this is about convolution, and let's look into the application of convolution and what convolutional neural network is. So okay. So convolution is the building block of most of the deep learning model that we use in our image processing operation for the entire computer vision pipeline. And convolution neural network are basically the neural networks which are specialized for detection for detecting visual patterns or the features from the images. For example, if we use if you what's the meaning of feature, if you may ask. So let's say let's go back to our kernel, and let's take another image. Let's say let's take an image of a cat. We'll go over to the canny filter, and yeah. Okay. Just a moment. So let me import an image of cat. And let's perform a canny filter on that image and see what we will, let's see what we get out of it. Quite a large image. So this was the input image of our cat, and we wanted to understand what feature really is. So features are nothing but the functional elements of an image. For example, in this case, the functional elements in this case are its whiskers, its eyes, nose, and ears, and they have a certain geometrical shape due to which we are able to understand it visually. So when we apply a canny filter to this image, what we get over here is the original image, and what we get over here is all the edges that are being detected. For example, the eyes, the nose, and the whiskers. And these are not complex operations that are being done or any functional changes that are being done. These are done solely based on convolution using a simple kernel and trying to extract the features from the image. Now what we wanted to do is we want to say that, okay, this element that we extracted from this image it belongs to whiskers. This element that we extracted from this image, this over here, this circular thing, is an eyeball, or this triangular thing is a nose. And how we move from extracting features just based on simple calculations to getting more intelligent results about an image. So for that, we rely on CNN. We basically we basically create a simple classification. So starting from getting the feature from an image to classifying those features as some named values, let's say whiskers, nose, ears, or whatever. Then we try to classify the image as a cluster of a bigger of a bigger hierarchy. Let's say if these are the features that are being extracted from this image, this belongs to a cat. Now these are the features that are being extracted from an image. This image belongs to a dog. So there we talk about image classification. Now, what image classification really is, and why we need image classification is because sorry, yeah. So what we do in image classification is we try to process images and we categorize them into different bin values. We can do a binary image classification like simple cat and dog case, or we can do a more complex image classifications. For example, if we are looking at the image of let's say a CT scan, we have thousands of images or millions of images, and based on that we want to say that whether there is a probability of a cancer in the patient just looking at those images. So these are different image classification operations that we can perform. It goes on from a whole range of spectrum, from binary to a multi-class classification. We will, for the sake of this workshop, we will try to work on with a binary image classification, and even creating a binary image classifier is quite challenging, and we will see how we will sort of try to unroll it. So, well, image classification is, again, it is ubiquitous. When initially when we talked about healthcare, autonomous driving, e-commerce or surveillance, we need to classify the object or that we detect in the within our camera or within our microscope or within our CT scan or X-ray, as we need to provide it a certain label. We need to put it into a certain bin in order to know in order to do the other processes followed by classification. And the standard image classification models are of, basically they are of two categories. First one are simple traditional models in which we just do the feature extraction and we perform certain machine learning algorithms on those features to get an insight about the objects in the images. The second is are the other models which are more complex, which are developed in recent decades, which are deep learning based models. They are particularly talking about the neural network models or the CNN that we initially talked about. So in case of traditional image classification models, the steps that we follow are the following. First, what we do is we extract the features from the images. For example, let's say we extract the color, let's say we extract the texture or the histogram from the image. The second thing that we do is we choose the most informative features. For example, in case of our cat, we had a number of things that we got, but we want to choose the most informative feature. We want to know that which these white lines that we get in the image, which of this belong to which part of the white line belong to whiskers, which part of the white part belongs to the eyes. So we want to select or choose the most informative feature. Then the third thing is we create classifier in a way that we train our model using a certain training data set, and based on the training data set we label the data. And then what we do is when we have trained our model, we use it, we take any random input image and we try to do our usual classification. So this is how a standard or a traditional machine learning based image classifier works. But in recent times, when the quality of data is humongous, and by humongous I mean the training data set is humongous, and we want to do image processing, or we want to apply some computer vision tasks on some abstract images. What we need to do over here is we need to create abstract features. So in case of traditional models where we created features like, let's say this belongs to whisker, this belongs to eye, where we label the data and then we try to do the classification. Instead of that, in deep learning models, what we do is we automatically learn the relevant features from the data. We create a large training data set and we extract abstract data from the images, from the data automatically, and then we perform the task. Then we try to derive insights from the data set. The advantage of deep learning model instead of a usual image classifier, that traditional image classifier, is that it doesn't work in a linear fashion as we saw. It works as like end-to-end learning. So in case of CNNs, convolution neural networks, they learn hierarchically from the raw data. Then what they do is they basically try to derive insights from the data, and it automatically does that. It automatically abstract the features from the images, and then it tries to like adapt itself to the relevant features. The most important part of the deep learning model, of these deep learning models for image classification, is that it is suitable for both large scale and small scale data set. In case of our traditional models, we can't apply them to a small data set. For example, we have a very small training data set, and we have a very limited number of labels, or we have a very limited number of features that we can assign to those images. In those cases, traditional deep learning models won't work. They would fail. Therefore, we need something like a deep learning model, which is quite robust in terms of feature extraction, labeling, and classification. So, talking about the most important part of the entire talk is the convolutional neural network. I guess a lot of you might have heard about it. So, a convolutional neural network is basically it consists of three units. First is extracting the features, as we talked about, then classification, and then the third part is assigning a probability to those classified images. For example, let's say we take an image of this. We take an image of Tweety, and we want to we have a convolution neural network, and we want to detect what character this really is. So what it will do, it will create these feature maps which consist of the featured maps, which consist of the following operations, starting from convolution. So at the core, we are doing the convolution only. So we start with convolution, then we do the pooling, and then convolution, and then again do the pooling. And in the last layers, we basically have these fully connected layers, which gives us an output, and these outputs, they belong to a certain class, and the end result of a CNN is basically a probabilistic distribution. And based on that, we say that whether the image belongs to the class 1, class 2, or class 3. For example, in our case, the class 1 was Donald. Sorry. For example, in our case, the first class was Donald, the second class was Goofy, and the third class was Tweety. So when this we performed the image processing on this image, and we fed it to our model. Keeping in mind that this model was already trained from previous data set, let's say there were millions of images of different cartoons with certain labels. Then what we do is we take an input image, a random input image of Tweety, and we wanted to see if this image is Tweety or not. So when our entire pipeline does the calculation, the end result that it gives is the probability values corresponding to the classes. For example, the probability that it belongs to Donald based on the features that it extracted is 0.2, Goofy is 0.1, and Tweety is 0.7. So we say that okay, it is more than 50%. So yeah, the probability that it is Tweety is large. So yeah, that's all about CNN models. And so the three main advantages that we get out of deep learning based model is that the first is regarding the feature extraction. As I mentioned you previously, the manual feature extraction is being done in case of traditional models, but in case of deep learning models, the features are extracted in a more abstract manner. For example, what it really means is in case of when the CNN was being used to detect the image of Tweety, it didn't create a feature of an eye. It didn't create that. It didn't create a feature where it says that if there is a black circle and if there is a green area surrounding that black circle, it would be counted as an eye. It created an abstract feature which we really don't have an idea about because these networks are sort of the black boxes. We can peek into it, but on a fundamental level, they are really very abstract. We don't really have any information about it. But what the benefit of that is that it automatically creates these features. For example, if there was another feature on this face, for example, there was a mole over here, and we in case of traditional models, we have to define that okay, this is a mole. But in case of convolutional neural network, it would automatically consider that as a feature. There is one problem though, that sometimes it creates feature out of something which is not actually a feature, or in that case we need to tweak and we need to see if there is an overfitting, underfitting, or what we can do over here. That we will look into the later part of this workshop. The second most important part is the data requirement. In case of traditional models, we require a lot of data. We need to also engineer our data from the data that we already have. But in case of deep learning model, it learns from the data. Once it learns from the data, it can work with a smaller data set by itself. The third part is with performance. Since the deep learning model is much more complex, and it also requires a lot of computational expense. It works on a lot of computational expense. The performance is much better, right? So that's why deep learning models are much better than convolutional neural networks. Now we will do a simple exercise. I will ask you guys to code along with me. So what we will do over here is we will try to create a simple dog and cat binary classifier in our worksheet. And we will use a data set that we have already. Quickly jump over here. Oops. Shut it down. So what we are going to do is we will take a data set for cats and dogs, and we will try to create an image classifier for it, a binary image classifier for it. So the data set that we are going to use is public level Kaggle, and this consists of around I guess 50,000 images of cats and dogs, and we will try to create a classifier out of it. So the first thing that we will do over here is quickly get the data set on our Google Colab worksheet. I would really appreciate if you guys can also code along with me. If you have any problem, you can. If you face any error, just write it in the comment section. So yeah. So this is my previous notebook that I was working with. So we will just get this data set from Kaggle. So this, so if you have worked with Colab, you know that you need to import the data over here as we are doing it for the previous images. But if the data set is quite large, you can't really import it. You can sort of mount it on your drive, but it's much better if you just get an API from the data set that we already have, and then work on the data accordingly. So what we will do over here is this data set which is publicly available. We will get the API. We will get the API call, and we'll just get the data set directly from there. So in order to get the API, you need to sort of go to your Kaggle profile, and go to your account and get a JSON extension. You just need to create a new API token, which is basically downloaded over here as a JSON file. What you need to do is, instead of downloading this entire, let's see how big is this data set. Yeah. So this is 1 GB, so it's quite large. So instead of doing that, what we will do is we will just get the JSON extension over here. Let's see, we downloaded it. I'll mount it over here, and I'll get the API keys from here. So you just need to copy this command to from your Kaggle dataset, which is over here. Just copy the API command, and you will get the dataset on your drive. I'm Just copy it from here, the one that I was working previously with. Okay. Yeah, it is mounted perfectly. For this, okay. So now we have got the data set, and we will try to work on this images. So this Kaggle JSON file is basically we need to unzip this data set, and we'll just import zip file. We'll give as a reference. Here, the zip file API. Let's copy the content. I'll just get it. Just copy my path over here, and yeah, just copy the path. Okay, there's some error. Oh, the API key is not working. Let's fix it. Just call it out again. So, let's go. Okay. Let's see if it is working. Yeah. Okay, how is working? Let's see. It should work. I'll try to run down another notebook. I think there is some problem with this. It's being shared, that's why. Yes.
Sorry for the interruption, everyone. The speaker is facing some network issue. He will be right back.
Okay. So guys, am I audible? Yeah, cool. So sorry for the network issue from my side. So what we were trying to do is we were trying to build a simple classification model for a number of images that we had. So what we did was we took the dataset from the Kaggle and we just got the API keys for the dataset. We basically mounted a JSON file of we'll just import the JSON file, mount the JSON file on our terminal, and we can get the dataset from there, right? So after that, what we will basically do is we will import those files. So basically, this is still in a zip format. We will unzip those files, and we will get the data set, or basically we'll get the images of or images from our uh, from the JSON file that we imported. So let me just show you what the images really look like. If you can have a look at it. Yeah. So this data set called cat versus dog, it has around 50,000 images of category 1 and 50,000, roughly 50,000 category of category 2. Uh, Oh, sorry, not 20,000, 2,500. 2,500 images of category 1 and 2,500 images of category 2. Uh, for example, you can look at them over here. This is what the image data set looks like. So what our model will do is it will extract the features from these images. So this is the first, so we are doing the binary classification, right? So what our model is going to do is it is going to extract the features from each of these images and classify them into one category. Similarly, it will take the features from the images of the cats and classify them into another category. There would be a training curve associated with it, and there would be a validation curve associated with it. So we'll quickly have a look into it. So in order to do that, we'll first import the, we are going to use TensorFlow library to run the model, to create a model basically. So we will import the necessary libraries over here. We'll import TensorFlows and Keras. Keras is generally used to deal with the sequential data set that we have over here. And as I mentioned to you previously, CNN is basically really good for dealing with data set which are grid-like. Grid-like means a matrix, like an image. So we will take that data set from. So we'll take that data set. We will, before directly getting all those 2,500 images, before feeding those 2,500 images directly into our model, what we will do is we will create something called as generators. Well, generators are used to handle the large data sets and create them into smaller batch sizes, so that instead of training the entire 2,500 images, we are creating a batches of around 32, 32, 32, so that would be fed to our CNN architecture. So we created these generators. We imported the image. We basically got the data. We created generators, and we will create a validation directory for this. Validation directory is basically it consists of the labels that we want to infer to it. So in our case, since there are only two classes, so we are taking 0 as the class for the cats and 1 as the class for all the dogs, right? So when I just ran this file, I got around 20,000 files belonging to class 2 and 5,000 files belonging to classes So this is for the generator part, and this is for the validation part. So basically, we divide our data set into two parts: training and test. Training and test. So we take around 25% of the data as our validation data, and we will proceed ahead with feeding that data into our model. Before feeding our data set to our model, what we need to do is we need to normalize the images, right? So as I might have shown you earlier, what the images really look like is this is like how the computer interprets images, nothing but the pixel values from 0 to 255. What we want to do is we want to normalize these images, and we want to normalize these values from, instead of 0 to 255, we want to normalize it to 0 to 1, right? So instead of directly feeding it to our CNN model, what we will do is we create a process function. In this process function, we will feed the images, all the images that we have, and the labels, the two labels that we created initially, and it will take these inputs and it will normalize those images. It will transform those images from a pixel value of 0 to 1 instead of 0 to 255. So this is what this process function does. And again, we will create a training data set and validation data set for the same. The process function takes that, transforms that, and then using a map function, we basically create the directory for training and validation. Now it's time for the main part of this exercise, is building the CNN model. What we will do over here is we will use a kernel size of 3x3, the convolution that is being done to classify the images into the size we want. We can change it to 5x. We can change it to 5x5 or 9x9 in order to get better efficiency. But in case of binary classification, since the difference between the two classes is very obvious, so the kernel size needs to be quite smaller in order to do it more fastly in a faster way. So we will create our model. We will create it by using 3 layers. The first will consist of 32 neurons. The second would consist of 64, and the third would consist of 128. So this is what our hierarchy would look like. Then what we will do is we will add something. We will add the activation as ReLU activation. It is basically an activation function that we give to the last layer in our CNN model. If you have, if you remember the architecture of the CNN model, this is what it looks like. As you can see over here. So these are the convolution layers. This is the last or the flattened layer where the classification actually occurs. So so these 3 layers we have defined for this model. This is the first layer of the model. This is the second layer of the model, and this is the third layer. Along with this, we are also doing the batch. We are also doing the batch normalization. So it is basically performing the normalization over each batch that we created, the batch for 32 images that we created, and we are doing the batch normalization. What the batch normalization does is it basically improves the efficiency of creating heterogeneous classes. So basically what our CNN model will do is it will extract abstract features and then classify them and then cluster them into 2 classes based on a certain algorithm. Batch normalization will improve this efficiency for each batch of the images which are being fed to this to this data set. And along with that, we will also do something called as max pooling, which is also a pre-processing operation that we have to do on these images. So using these two operations, we will basically enhance our already existing layer of our CNN model. And after these three layers, we will add the a flattened layer, and followed by that, we will need three dense layers with activation function, with a ReLU activation function, and a dropout layer with a factor of 0.1, and the last layer with sigmoid sigmoid activation function to classify them as 0 or 1. So so when we will run this model, we'll quickly look into the model summary. What are the parameters? We just need to we just need to check if all the parameters are correct, and all the files that we are feeding it are correct or not. So from here we get that there are around 14 million sort of 40 million parameters over the case of our entire data set, in which roughly 488 are non-trainable, which is quite okay. Then what we will do is we will compile it using an optimizer called Adam optimizer, and we will use binary cross entropy, and we will also use a parameter called matrix to calculate the accuracy of our model. Then what we will do is we will try to fit this model with the training data set, right? So what we are doing over here is we have created two classes. We have an entire data set with extracted features, and this is now being fed to our model to create two binary classes. These binary classes, the model, when this model would be running when the data would be fed to the model, it will create these two distinct binary classes, and we will store the data as history, because we want to retrace back, and we want to have an idea about how much what is the accuracy of our classification, right? So this epoch is nothing but the number of iterations, number of times we want to run this model. So as you will see, when we initially as we increase the number of epochs, the accuracy generally increases. So initially, when we ran this model, accuracy is basically ability to cluster between two different images. So two different classes. For example, it took let's say it had around 20,000 images. In those 20,000 images, it used around 5,000 images to train it in a single go. Then what it did, it took a few images and it basically clustered them into two classes. It had an idea about what originally these images were. For example, the computer already know that these two images are either cats or these are dogs, based on their initial labels. But when it fed it to the model and then it classified them, based on that, it calculated the accuracy of this model, that whether the classification is good or not. So initially the accuracy was around 0.60%, and then it improved further on, and with around 100 epochs, with around 10 epochs, we were able to get around 97% accuracy, which is quite good for such data set. And it is generally acceptable value for binary classification. Along with that, we also calculate the validation loss, and we also calculate the validation accuracy, right? So validation accuracy would be a little less than the accuracy with the accuracy. This accuracy is basically for the 20,000 images, and this is for our validation test data set. So after feeding this, we will basically store these history values in order to get an idea about what is the accuracy of clustering and stuff like that. So to get an idea about how accurate our model is, how efficiently our model is running, we will try to plot the accuracy with time, with number of epochs basically. So when we will try to plot the accuracy for our training data set and validation data set. So for training data set, it is quite good. The amount of data was quite significantly large. And within 10 epochs, we were able to get around 90% of accuracy, which was quite large. But for for our validation data set, which was quite smaller, around 4 times less than that. So the accuracy was quite low. It was like 80% is not that acceptable. But we can improve this accuracy. We can improve the accuracy. So the problem here is like why the accuracy was a little low was because there are chances of overfitting which was happening here. So basically, what CNN does is it takes the abstract features and then creates the classes or feeds them into or like matches them into the classes if the features that are being extracted are nonsensical. If let's say it is extracting the features which belongs to whiskers, but it is simply some straight lines which are present on the face of the cat, then that would be classified as an overfitting operation. So the overfitting would lead to less accuracy, and that is why we are getting a low accuracy for the validation data set. In order to improve the accuracy, we can do a number of things. For example, there are roughly 4 or 5 things that we can do. We can add more data set to our model, but we have already fed all the data set we have. We can do the data augmentation probably, but data augmentation is basically creating more data set from the data set that we already have. So basically, let's say we have an image of a cat or a dog. What we do is we perturb the image a little bit and we create our own data set from the data set that we already have, so that the batch size is much larger and the accuracy improves. Usually when we do the batch normalization, the accuracy improves much better, but data augmentation is also quite useful in that. Apart from that, L1, L2 regularization are the two methods that are generally used to improve the accuracy. Apart from that, as I discussed, the batch normalization can also be used, or else what we can do is we can also reduce the complexity of our model. Instead of using 3, 5, or 6 layers, we can reduce the complexity and see if we reduce the number of neurons within the layers that we are using, is the accuracy improving, or are we able to get a better are we able to get better results in terms of validation loss, right? So when we perform this operation, when we let it run for several minutes. So basically, when I trained it, it took me around half an hour to run this model on the GPU that is already available in Colab notebook. So if you are running it on your Colab, just make sure that you go to the runtime, go to change runtime type, and make it to GPU, T4 GPU, or whatever GPU that is available on your disposal. Don't run it on CPU; it will take a lot of time. The model is quite large, and the data set is a little bit humongous. So you need to make sure that you run it on GPU if it is not available to you readily. Then it takes around, I guess it took me around half an hour to complete this training. And what we will do after this is we will take a random image of a cat from. We can basically take an image, any image of a cat or a dog, and we can basically run it over our model to see what is the accuracy, or is it able to classify it properly or not. Let's say we basically imported an image of a cat, which from somewhere from the internet, and we just ran it over our model, and we got the result as Just run it. Yeah. So when we use the model predict, we got the category. So this the first element represents the category, and second is the type. So it shows the category as 0, which is absolutely correct. That's the image of a cat. So now let's see if we can get an image of a dog. We just mount it a little. Dog, okay, CV2 is not imported. It should work. Mm, yes. It should work. So this is the image of a dog, and let's see if it is able to give us. It should give us. Yeah. So this belongs to category 1. And this not working. But anyway, so this is how our simple binary classifier works. I'm sorry, I was not able to code while I was explaining it. I had to refer to an old file that I was already working with. It was some issue, but anyway. So this is how you create a simple image classifier. You get the dataset. You import the necessary libraries that are there over here. Then you create, in most of the cases, even in case of multi-category image classification, where instead of just binary classification, you have multi-class, a number of classes. There also you need to create generators in order to process those images. The second thing that you need to do is just check do some pre-processing on the images. For example, in this case, we did the normalization on the image, which is quite a standard routine that we follow. In some cases, we need to do something more with the images. For example, we need, let's say, we need to sometimes sharpen the images, especially in case of places where we are dealing with medical images, where most of them are blurry, and we want to extract a more sharpened feature of a certain area, or a certain region in the medical image. we need to perform some pre-processing like sharpening. We might have to do the edge detection and then superimpose the image over the original image in order to enhance the feature detection. And after that, we create our own custom CNN architecture. We define the number of layers based on what kind of data set we have, what degree of complexity we can incorporate, and what kind of computation power we have. Based on that, we create our model, and then we basically test it, train it, and we just look at some of the statistics of our model. We can like plot a couple of things, and based on that, we can get an idea about how we can sort of improve the accuracy. And then we can just take any image and see if our model is working or not. So yeah, that is all about creating a binary classifier for this session. You can refer to this. I will this file would be there in somewhere in the comment section, or I'll put the link over here so that you can access it. One task that I'm giving you, if you're watching this and if you have followed it, is what you can do to improve the accuracy of this classification. For example, in my case, the validation was roughly around 80%, which is not really good. So as I mentioned you, there are a number of things that you can do in order to improve the accuracy of classification. You can either do the batch normalization, which I already did. You can do some degree of augmentation. You can also add more data. We really don't need to add more data because we already had it. So maybe you can try some kind of augmentation over this image. Do some pre-processing. Do some apply some filters over the image that apply some filters as I mentioned you initially during this session, and then feed it to the model, and then maybe we can see that the features are more enhanced, and the accuracy would be much better. So yeah, that is all about this part. Let me quickly wrap up this session by quickly taking you over to interesting projects in computer vision uh, uh, related to whatever we learned today. So let me share it. Just a moment.
Deepak, thank you so for the amazing session. Audience loved your workshop.
Uh, Thank you so much. Let me just show you a couple of simple projects, some interesting projects based on what we learned today, and then maybe we can wrap up the session. Just give me a moment.
Sure, sir, sure.
Yeah. So as we were discussing about extracting features and classifying the images, now instead of classifying the images, we can what we can also do is we can also locate the features, right? So this was a really interesting project that we developed in which we did the facial recognition using computer vision using a library called MediaPipe. You can also use OpenPose or other stuff. And using MediaPipe, what we did is we created an AI-based assistive text solution for people with upper limb disability. So what this interface really does is it takes it basically detects the landmark points which are present on our face, and then converts those landmark points into computer commands, into meaningful computer commands. Someone who, let's say, someone who's disabled who don't have their hands, how they will operate a computer. So what they can do is their facial the landmark point of the facial movement is converted into the coordinates of the cursor. The right click and the left click is being detected as right blink and left blink of the eye. And if someone wants to type something, they can simply use on-screen keyboard, or they can also use something called a spy audio library that we integrated in that. So I'll quickly show you a demo video of how this really works. Okay, yeah. So So basically, in this you can see a user is is sitting in front of in the laptop, and his coordinates, his spatial movement is converted into the coordinates of the cursor. The right click and left click of the eye is being converted into the right. Sorry, the right blink and left blink of the eye is converted into the right click and left click. And if you want to type something, they can just use on-screen keyboard, or they can simply use a Pi audio library. So simply using this interface, the user was able to create. Let me show you the final result. This is much cool. So just using this interface, moving his hands around and head around, this was the final 3D model that he was able to sort of create in SolidWorks. Just using this interface, nothing else. And yeah, this solves a lot of problem. It can help people to design, even disabled people to design or to code or to do a lot of things that they want to do with the computer. So this was a really sort of a cool project, and oops. Okay. And this project went to a couple of places. Someone from Google reached out to us when we put it out. We basically created a simple UI for this application, and yeah. So and we sorry, and this we basically gave it to an NGO. Let me just quickly go through that part. So we created a simple prototype and we gave it to around 100 people. We basically collaborated with an NGO and gave it to around 100 people. We recorded the data. We basically get the data set from those 100 users, and we got the feedback from them. Based on those feedbacks and based on their movement values, we basically changed the parameters of our model, and accordingly improved the accuracy of our. Let me just go back to the slides. Sorry. Yeah. So this was about the fifth film. We won an award by Google last year. Another interesting project which I started sometimes around my undergrad 7 years back was an interface using, and now instead of using the facial recognition or using the facial features, we take the features from the entire body and we converted those features into gaming commands, and this led to something called as Immerse 2.5. So we use the same CNN-based architecture for pose detection, and we converted them into computer commands. Now, instead of just using the facial commands, we use the angles of the body and converted them into gaming commands. And I'll show you a demo video of this also. So yeah, so we basically integrated it with GTA 5, and in the corner you can see as the user is moving, the player or the avatar in the game is moving out accordingly. It can even take into account the complex movements like running, or something more complex like let's say shooting or focusing, which is not possible with usual gaming gears. For example, if you will look at this video. Yeah. So if you sort of look at this video, you can see the user is moving his head and the POV is changing, the focus is changing, and you can do something like this. So this is pretty good. So it just gives us a more degree of immersion with the game using a simple uh, computer vision backend code. So yeah, so this was quite cool, and basically what we were doing over here, we were using the sequential data set from the frames that we were capturing with our laptop, and we were creating we were creating a category, or we were doing again classification problem. Like for example, based on what pose the person is making, we basically created classes of movements, either it is running, sprinting, shooting, or focus defocus, and yeah, and we just integrated it with the game, and it was pretty cool. And this was our model architecture. This is what our model architecture looked like. In our case, we had 3 LSTM layers, a few dense layers, and a last layers to create the category of the movement. And we integrated with a lot of things, not just games. We basically integrated with a metaverse of NIT Rourkela, and someone can just, we basically created a 3D version of an IT Rourkela campus, and integrated it along with that, and user can simply open the website and stand in front of the laptop and do a lot of things, can roam around the campus, so, which was pretty good. So yeah, so this was about the second project. The fun thing about it was someone from Facebook reached out to us when we developed this product, and they basically adopted this idea, and they took it further, and we sort of won an award by Meta. So this is how we can use very simple stuff using simple CNN models and create something really interesting. So yeah, so that is all about this session. I hope you guys had a good time, and yeah, let's wrap it up. Thank you so much.
So those were really amazing projects which you have made. Thank you once again, sir, for being with us, and it's really pleasure to have you here with us and sharing your knowledge. Thank you once again.
Thank you so much.
Now the attendants can ask questions about the workshop. Post any questions you have in the comment section. Q&A session is started now.
You can ask your doubt in the comments. We will pin it for you.
Yeah, so I can see a couple of questions over here. So I guess the first is computing power is further improved? Can computer vision achieve the capability of ChatGPT or become one driving AI models? So so ChatGPT is completely based on NLP, and we are here talking about mostly CNN models. But yeah, the accuracy is becoming much better with better models coming into the picture, and a better quality of data set that we have over here with us. The major roadblock to most of these models is computing power. If we have better GPUs and if have a much larger systems to process these images, we can have a better accuracy in no time. And talking about them being compared to AI models, well, the AI models or the generative AI models, for the sake of it, uses computer vision to develop images. So they basically, as you give the prompt to it and it generates an image, it basically uses the same concept of creating it. So yeah, so it is like in line with the speed of GPT or the progress of GPT in some sense. Can you use multiple data set for data sets in a program? Yes, we can use multiple data set. We can use whatever data set we want. I think his question is like, can we use multiple classes of data set to feed it to a model? So yeah, we can basically do that. Yeah. So how to use GPU instead of CPU in my system for trading? You can use Colab. So as I mentioned in the workshop, if you have been through it, in Colab you have the option to switch between GPU to CPU. With GPU, you have a limited access to GPU, but you can also get like an extended version of it with paid subscription or something like that. But you can still access GPU through Colab, and even through Kaggle you can access the GPU. So yeah. So, are the job prospect in current industry environment for someone who is willing to masters in AI and computer vision, and what kind of roles can expect? Okay, so if you are working in computer vision, there are multiple opportunities, as I mentioned you, in healthcare, in surveillance, especially in industrial surveillance. The jobs for a computer vision engineer is beyond the comprehension. They are like hiring like something else. Recently, I got in touch with a startup based out of Pune, where they are using computer vision to detect the compliances in the factory, in the assembly line. So in that way, you can contribute to that, and you can delve into multiple industry. You can also go into research, and furthermore, if you talk about the top tier companies, you can also look into how Meta is revolutionizing the space of immersion using computer vision. So you can also think about that. So yeah. Zero shot object detection. Well, I didn't include this in my talk. It is an entirely different topic. So maybe we can take the next question. So yeah. Are there any further questions? Does computer vision contribute to quality control and defect in manufacturing? Yes, it does. So basically, using computer vision, we basically track the shape, size, and even the qualitative picture of an object which is being produced in an assembly line. So it does affect to quality control and detect detection of defects in the manufacturing.
Okay, so this is the end of the Q&A session. So as we now near the conclusion of this incredible workshop, I would like to express my heartfelt gratitude to Mr. Rupesh Mahore for joining us today and sharing his expertise with the audience. In return, I would like to give you a little gesture of appreciation. Uh,
Yeah. So thank you so much, guys. Thank you so much for having me over here. It was great to interact with you and share my knowledge about computer vision and things that I have worked with. I really think that computer vision is the vision for the future, as we say. As new technologies will emerge, we need to look at the world from a better perspective. That's why we need a better tech in computer vision. So let it be generative AI, let it be autonomous driving, a better diagnostic of healthcare. We need computer vision, and I truly think that it is the vision for future. I would like to thank you guys for having me over here, and I'd like to thank the audience for their intriguing questions. I really enjoyed this session, and yeah, thank you so much for it.
Thank you, sir.
thank you. Guys, we have shared the quiz link in the
Quiz.
comment.
Please attend the quiz.
Yeah.
It will be based on the session from today. Make sure you take the quiz and compete and take the top rank in the leaderboard.
The top rankers will be rewarded after the session.
Yeah. So now let's look at sponsors. So our streaming partner is StreamYard. On StreamYard platform, you may broadcast over social networks directly from your browser. Before choosing the StreamYard Premier plans to gain access to more features, it provides a free option that you may check out.
Next up is HP. HP is a technical sponsor. HP Incorporated is an American multinational information technology company headquartered in Palo Alto, California, that develops personal computer, printers, and related supply, as well as 3D printing solutions.
I want to thank all the participants for being a part of this workshop. Before we call it a wrap, we hope you see you all at our next session on Cosmic Connect at 4 p.m. Thank you, everyone.
Thank you, everyone.